In this lecture, we show how one can apply Romberg integration to improve estimates that we obtained with the trapezoidal rule of the integral of sin of x squared from x equals 0 to x equals 2. To apply Romberg integration, we use a uniform partition for the interval of integration. Let n be the number of subintervals so that the step size delta x or h is equal to 2 minus 0 divided by n, or 2 over n. Let t sub n be the trapezoidal rule estimate of the integral. Then t sub n is given by this formula. The exact value of the integral can be shown to be equal to t sub n plus some error terms. The first error term is c sub 1 that depends on h times h squared. A long established fact extends the error terms to include c sub 2 that also depends on h times h raised to the fourth power. For a proof of this equation, we refer the viewer to a video that we had prepared, the title of which is the Trapezoidal Rule Integration by Parts and an Extended Error Formula. We are including the link to this video in the description of this lecture. It is because of the inclusion of this fourth-order error term that we will obtain three different estimates for the trapezoidal rule. We will first obtain the trapezoidal rule estimate, t sub 32 with 32 subintervals, followed by t sub 16 with 16 subintervals, and then t sub 8 with 8 subintervals. This way, after finding t sub 32, we can just reuse some of the y values from t sub 32 instead of recomputing them to find t sub 16. We will also reuse some of the y values from t sub 32 to find t sub 8. This is to avoid accruing calculation time, which is a general practice when coming up with numerical algorithms to solve more complex problems. We are implementing this practice in this exercise, even though accruing calculation time is not going to be an issue with our rather simple exercise. In the error formula, c sub 1 and c sub 2 will behave like constants for sufficiently small values of h, or for sufficiently fine partitions of the interval of integration. We will assume our partitions are fine enough, so we will regard c sub 1 and c sub 2 as constants, so that the equation for the exact value is really an approximate equation. We are going to use the software Mathematica for this exercise. F of x equals sine of x squared. The step size h is 2 over n. We start with n equals 32. So h is 1 over 16. Since the x values are not directly involved in the trapezoidal rule formula, we go straight to defining the y values. We call the list of y values y-vals. And we use the table command. So we have the table of f of x. X goes from the left endpoint 0 to the right endpoint 2 with step size h. We store the value of t sub 32 in the variable t32. t32 is equal to h over 2 times the following quantity. Inside the parentheses, we'll single out the y values at the endpoints 0 and 2, since they're without the coefficient 2 that the other y values have. F of 0 is the very first y-vals value, so it is designated as y-vals double bracket 1. With 32 subintervals, there are 33 partition points, so f of 2 is the 33rd y value, so f of 2 is y-vals double bracket 33. For this part of the trapezoidal rule formula, we have 2 times the sum of y-vals double bracket I, with I going from 2 now that the index 1 had been reserved for f of 0, and I goes all the way to the index n, or 32, since f of 2 has index 33. We write almost exactly the same command line for t sub 16. We simply tweak the value of h and the range of the index I in the code. So we write t16 equals the step size, which is now twice h, since the subintervals for t sub 16 are twice as long as those for t sub 32. 2h divided by 2 is h. To this, we multiply the quantity with f of 0 and f of 2, which are respectively y vals double bracket 1 and y vals double bracket 33, followed by 2 times the sum of y vals double bracket I. Now for T16, I should start at 3 since each subinterval is now twice as wide. And I should end at I equals 31. We should also remember that this time the index I jumps 2 steps at a time. T sub 8 doubles the step size of T sub 16 and quadruples the step size of T sub 32. So the step size for T sub 8 is 4h. 4h divided by 2 is 2h. So T8 is 2h times the quantity with again y vals 1 plus y vals 33. Then we have 2 times the sum of y vals double bracket I. This time I starts at 5 and ends at I equals 29. I also increases by 4 at a time. We evaluate all the lines of code. And voila, we have T sub 32, T sub 16, and T sub 8. We now apply Romberg integration and work with the error terms. We bring back the relationship between the exact value of the integral, the estimate T sub n, and the error terms. Since for small values of h to the fourth power will be much smaller than h squared, we first ignore the h to the fourth power term and use this approximate equation. Using the value we found for T sub 32, we have the exact value of the integral is approximately T sub 32, which is 0.803924, plus T sub 1 times the square of the step size, which is 1 over 16. Using the value of T sub 16, the exact value of the integral is approximately 0.801352 plus C sub 1 times the square of the step size, which is now 1/8. Using the value of T sub 8, the exact value of the integral is approximately 0.790821 plus C sub 1 times the square of the step size, which is now 1/4. Solving these two equations simultaneously, the exact value of the integral turns out to be approximately 0.804781. C sub 1, by the way, according to these equations, is approximately 0.219. We'll refer to the new estimate of the integral as Rom sub 3216. Solving these two equations simultaneously, the exact value is approximately 0.804862. C sub 1 this time is approximately 0.225. We'll refer to this estimate of the integral as Rom sub 16.8. This first step in Romberg integration is supposed to deal with the order h squared error term. More precisely, it is supposed to eliminate the order h squared term so that we are left with only the order h to the fourth power term. So replacing T sub n by the improved Romberg estimates, and disregarding this time the h squared term, which we are supposed to have just eliminated, we end up with these equations involving Rom sub 3216 and Rom sub 16.8. From this equation, the exact value of the integral is now supposed to be equal to the estimate Rom sub 3216, which is 0.804781, plus the error term, which is now C sub 2 times the step size raised to the fourth power. For the value of h, we use the finer step size between T sub 32 and T sub 16, and that is the step size for T sub 32, which is 1 over 16. We also have that the exact value of the integral is supposed to be equal to the estimate Rom sub 16.8, which is 0.804682 plus the error term. We again use the finer step size, this time between t sub 16 and t sub 8. T sub 16's step size of 1/8 is finer, so the error term is c sub 2 times 1/8 raised to the fourth power. We solve this system of equations and find that the exact value is supposed to be 0.804776. We did carry out exact integration with Mathematica, and the exact value up to 6 significant digits turns out to be this value.